right, I think we are live on YouTube, we are live on Twitter, and we are live on Twitch. Let's confirm. Yup. Okay. Let's go ahead and get started. Let me spit out this gum. Take a sip of this yerba mate here. And let's announce it. Good morning, Ed. Welcome to another Hoopo stream. Today we're going to be looking at interstellar spherules. Spherules. Not exactly sure how to say that one, but this is going to be a review of this paper here. This is a paper that was released on the 29th of August, 2023. This is a paper written by kind of this guy called Abraham Loeb. His name is actually, I think he's usually referred to as Avi Loeb, but this is a guy from Harvard University, specifically the Department of Astronomy, and he's kind of known as the alien guy because of this paper, because of other things that he's mentioned, but if you're watching this stream for the first time, you can find all the links that I will be showing here on this GitHub here, Stream Docs. Okay, so doing something a little bit different this stream. I already went ahead and read this paper, and I kind of highlighted some things, pulled up some stuff, and we're just going to kind of go through it. So maybe it's not the full kind of 2-hour deep dive that you guys are used to, but it should be a little bit more on point, a little bit less reading. Good morning, John, and good morning, Josh. So this paper is a collaborative work between a variety of different groups here. You got everything from Harvard, you got UC Berkeley, PNG, University of Technology, which I think is the Papua New Guinea kind of university. And you can see kind of here everything from Earth and Planetary Sciences, interstellar expedition, astronomy, mining, chemistry, chemical biology. So this is definitely some credentialed people from some reputable institutions. So it's not just some random guy in his backyard. This is a lot of people that are putting their name on this paper. So in this paper, they went out and they basically gathered a bunch of spherules, or basically these little metallic spheres. So this is kind of a picture of one in the thumbnail. They have pictures of them all throughout this. Here's a spheral, kind of like you see that little metal sphere here in this pile of collected material. Let's see if we can find another nice picture of this spheral before we go further. They have some nice pictures throughout this paper. I'm going to have to get better at scrolling. Here we go. Here's a picture of a nice little spheral, and here's another picture of a nice little spheral. So why is it a spheral? Basically what happens is that whenever something enters Earth's atmosphere, it'll kind of vaporize because of the drag, right? So meteors come into Earth's atmosphere. The air, you could think of it as kind of like water, right? And it creates this drag force, and that drag force eventually heats up the meteor, and eventually just it kind of explodes or vaporizes. And when something that's very metallic like that explodes, it kind of explodes into this mist of molten metal, and the little particles of mist in that molten metal tend to form little spheres in the same way that raindrops tend to form little spheres, and those little spheres then harden, and then they drop into the ocean. And that's what they did. They went and they collected these in the ocean. So they found about 700 of these and they're very, very tiny. They're only 1.3 millimeters in size, and they scanned roughly 26 kilometers squared of seafloor. And I went ahead and I looked up what kind of an intuition around that. This is around 50,000 ping pong tables. So if you had 50,000 ping pong tables in size, that's kind of the area that they sampled. So where is Manus Island, Papua New Guinea? I actually plugged in the exact coordinates, and this is where it is. So it's basically Papua New Guinea is part of this chain of islands here that kind of extends from the south of China and the kind of southeast of Asia and goes towards Australia, and then basically there's this huge amount of ocean here, right? This is where Hawaii is and so on. But north of this island here, which is Manaus Island, right about here, this is where they basically scanned. And what do they mean by scan? So in terms of scanning, what they did is they basically dragged a magnetic sled. So here you go. Here's a magnetic sled design. It's basically a big flat piece of metal with a bunch of neodymium magnets inside of it. So each of these little circles here is basically a neodymium magnet. 200 kilogram sled. So really heavy sled with a bunch of magnets on it, and they just kind of trawl it over the bottom of the ocean. And of course, any kind of metal thing is going to stick to it. Okay. So how do they even decide on this place? Like, how do they pick this place? So the way that they pick this place, it's based on the path of bolide. Bolide is just, bola means ball, right? That's the root word, the etymology for the word bolide, but basically it's just a meteor. CNEOs, and I had to look that up. CNEOs is, here's a conversation with ChatGPT, is the Center for Near-Earth Object Studies, which is part of NASA's Jet Propulsion Laboratory and is responsible for the studying and monitoring of celestial objects that come close to proximity to Earth. So basically CNOS, they keep using the word CNOS catalog, so I think that there's basically a catalog that gets released that contains all the different asteroids that impact Earth and where they impacted and so on. So basically they know that there was this asteroid in 2014, so January 8th, 2014, and then they know exactly kind of where it landed, and then apparently they also had sonar sensors in the water at some point near this place, and then kind of triangulating all of that data together, they know that exactly where that asteroid largely landed, which is pretty crazy. I didn't realize that you could pinpoint the location of an asteroid like that, right? The bolide broke apart at an unusually low altitude of 17 kilometers, corresponding to a ram pressure of around 200 megapascals. This implies that the object was substantially stronger than any of the other 272 objects in the CNOS catalog. Okay, so they know that this object, this bolide, this meteor, was extremely strong, right? It managed to get through a significant chunk of the atmosphere before it kind of vaporized, and that tells you something already, right? If it was made out of fragile elements, it would have broken up pretty quickly. So the fact that it managed to sustain a large amount of pressure and made it a very kind of significant stride into the atmosphere means that it was dense, right? It's made of strong metals, right? Okay, so based on the delay in the arrival time of the direct and reflected sound waves to a seismometer located on Manus Island. So not only do they have kind of the satellite and kind of atmospheric data, but then they also have water they have seismometers, which detect vibrations in water in a medium or also in Earth, and then they have those near there, so that's how they were able to triangulate the exact kind of final resting place of this meteor pretty accurately, right? So it's right there. Okay, so they also know that U.S. Space Command, which is kind of crazy that we even have an organization in the U.S. called the U.S. Space Command, but basically, they certified, so this is the government saying that this is a 99.999% likelihood that the object was interstellar in origin, right? So that doesn't necessarily mean aliens, right? Interstellar just means that this meteor, which we know is very heavy and very dense, is interstellar. Based on the velocity, right, this 60 kilometers per second, it's not coming from our galaxy. It's coming from... it's not coming from our star system, right? Our sun. It's coming from somewhere else, right? So it could just be some random passing by rock, or it could be, which is kind of the insinuation of this paper, it could be potentially a Voyager, right? So, not this. We want the Voyager probe. So the U.S. government a long time ago, back in 1977, released this probe called the Voyager probe. And what this is it's basically a message from us to someone else in the solar system, right? And it basically contains a bunch of information of like, here is Earth, here's a bunch of songs from Earth, and here is I don't know, some samples from Earth. But the thing is that this entire thing is made out of metal, and it's just kind of shot out into the galaxy, right, in some random kind of direction. So what this Avi Loeb character, the guy who wrote this paper, is insinuating is that maybe this meteor is the Voyager equivalent from some other civilization, right? Maybe it's a very dense metal object that was launched by some other civilization a long time ago, and it just finally made its way and crash landed here on Earth, right? He doesn't make that assessment in this paper, right? He doesn't even mention the word alien or alien civilization or anything like that. This paper is very sober, very scientific, but that's kind of why there's some hype around this, is that maybe that's what it is. Maybe it is a piece of an alien spacecraft. Okay. Good morning, Yujun. So they know about this meteor. They know where it landed. And then they go and they trawl the seafloor with this magnetic sled and basically pick up these little spherules, right? So a couple other points here. They're organized and funded by private contributions. So this isn't Harvard. He didn't go and get a government grant to do this work. Someone paid him money privately. So that's another kind of interesting part here, where he had to go out of his way to get the money in order to do this. So over the course of, I think, 14 days, they basically trawled this magnetic sled for around 8 hours per run. And then they did that 26 times total. So over 14 days, they basically trawled this sled 26 times. And you have a map of basically all the trawls. So here is all the different trawls. And the red square, so this is kind of like a top-down map view, and it's showing you the depth of the ocean, and it's also showing you each of the trawls. So you can see here that they did test trawls, right? So they know that the meteor landed inside this red square, right? So the red square is the uncertainty on the Department of Defense, which is based on the seismometer and the atmospheric and satellite triangulation, right, of where this meteor landed. So the Department of Defense is telling you it landed here in this red meteor, and they said, okay, we're going to make a box twice that size. We're going to make this green box. So we're going to search in this green box, which is 2 times that uncertainty given by the Department of Defense. And you can see how they basically, these are the paths that the sled took. They trawled a bunch of paths there, but then they also took some kind of control paths. So here, path number 22 and path number 17 here, what they want to show here is they just kind of want to test what the water is supposed to, or what the seafloor is supposed to look like, right? You need something to compare against. You need that control. You need that baseline. So they want to compare how many of these metallic spherules are we picking up here inside the meteor path versus outside, right? If we just go and we trawl some random part of the Papua New Guinea ocean, we're going to pick up some pieces of metal here and there. You know, maybe there's some boat or something that crashed, and then the boat, there's pieces of the metal boat down there. So they need some control just so they have an idea of like what the spheral concentration looks like outside of the region. So that's kind of this drawing here. I think they have another nicer map here. So this is an even denser map. So here they show you the density of the spherules at every single kind of like point. So here you have latitude and longitude, and you can see that the actual density, so this is once they've already done all the trawling and they've basically meticulously recorded, here's where every single spherule came from and where we found it, and you can see that there's kind of a region of high density for the spherules right here, which kind of corresponds to within the area of the red box that was given to them by the Department of Defense in the CNOS catalog. And just to kind of sanity check, you can see here on the control paths, so the paths that they took of a random part of the seafloor, just to compare against, there is basically no density. So you can see here, both of these paths, there really isn't that much density there. So with that, they've kind of basically confirmed that, okay, these pieces are very high likelihood from this meteor that we saw, right? All of those pieces together kind of confirm that that's probably what these spherules are. It's not some random spherule from some guy who dropped it off his yacht or something like that. These are very clearly coming from this meteor, or at least to a high confidence. What else have we got here? So he does some calculation of the actual spheral density. So, for example, he does that based on the total number of spherules, the weight of those spherules, and the estimated spheral density is that, which we just showed you. I think the picture kind of is the clear version of that. What else we got here? We assign each GPS, so they're very meticulous in this paper about kind of error bounds. So every kind of measurement has an appropriate error bound. So, for example, the GPS location has an error bound. The way that you're kind of dragging this sled on the back of the boat, you don't really know exactly where the sled is. You have a very accurate GPS position of the boat, but the sled is kind of like bumping and sliding around on the ocean floor. So there's a little bit of an uncertainty around every single sled position. But it's not a huge deal, right? Because it's what is 2 kilometers of uncertainty when you're dealing with this giant area of ocean, right? But it kind of goes to show you that every part of this paper, based on what I've seen, is very meticulously, they have all the different error bounds. So they're being very careful with the science here, which is a good sign. How's it going, Randion, Joseph, and Khalil? Randion, we still haven't confirmed that this is at all related to aliens, but we're working on it. So here are the spherules that they found on each of the different runs. So you can see here the date that they did these runs. You can see that they were roughly here from the 14th of June 2023 to the 27th of June 2023. They did 26 total runs, and you can see for each run the different spherules that they found. So this one here, run number 8, was actually the most productive run, where they found a huge amount of spherules. And we can actually go and see the exact run on the map. So run number 8, which was the most successful one, is actually back here, and you can see it kind of goes straight through this red area here, which is where the meteor landed. And you can see here that the ocean is actually quite deep. So this is the depth of the ocean, and it's over 2,000 meters deep, basically. It's around somewhere between 1,200 and 2,000 meters deep. So this is not a casual ocean depth, right? You're not going to dive that, right? If you're doing like diving, you're kind of like topping out at like 40 meters, right? At least that's the diving that I've seen and done. But 2,000 meters, there's no human down there, right? Okay. So that's what we have in the story so far. If we keep going, given that the highest yield yellow regions in the heat map account for roughly twice the background yield, owing to the excess spherules, right? The background yield is how many spherules they were able to get outside of this area, right? So the control sled runs, those are what they call the background yield. We expect to find a significant number of IM-1, which is the meteor, or the potential alien spacecraft, relative to the background spherules in the highest yield regions. And that is what they found. A significant fractions of the spherules in the yellow region are of interstellar origin. Okay, here's a little more zoomed in version of that. Here's that run number 8 right here, that mythical run number 8 where they found a huge amount of spherules, and you can see how they found a bunch of them there, and you can see here run number 13, maybe they were trying to get more, and so on. Kind of weird that the error region, the red box, comes from the DoD, the Department of Defense, because the DoD is the U.S. government organization that is kind of implicated in a bunch of this alien stuff, right? So the DoD is the Department of Defense, and a huge part of what they deal with is basically nuclear safety, right? So basically, like, are we getting attacked? Is there nuclear missiles coming towards us. So the DoD is the organization and the group within the U.S. government that has all these sensors all over the place to know whenever stuff is entering our atmosphere and where exactly it enters our atmosphere and how fast it's going. So that's why the DoD data is there. Okay. All right, so now we go into this next section here, and in this section, he kind of mentions that retrieval of cosmic spherules from meteor sites has a long history. So this isn't something like new, right? This idea of going into and trying to find the basically the metallic vapor of a meteor. People have been doing that for a long time here, and he drops all these papers here. So you have papers going from all the way 1979, 1991, all the way to 2017. So this is not some random weird idea. This is like something that people have been doing for a long time, where you go and you collect the spherules, and then you analyze the spherules, and then that tells you about the meteor and what's going on there. And of course, the spherules here are substantially different from the spherules collected in the control areas, which is how they're kind of showing that these are coming from that meteor. Here you have the different spherules, and specifically the ones that end up being super interesting are these ones here, B, L, A, U, and these are 3 different elements. So B, L, A, and U are beryllium, lanthanum, and uranium. So these are kind of rare elements. Of course, you can find these elements on Earth, but they're kind of weird, right? They're having metallic spherules of this particular composition is not something that you necessarily find casually, right? It's not something that is common in aviation components or electronics or trash of any sort, right? This is like very weird kind of elements, and they find them in these spherules in the exact place where you have this interstellar object that exploded and vaporized and fell into the ocean. Okay. And by the way, this conversation is also available on the Stream Docs links. So down here, conversation with GPT, if you guys want to see that. You can actually share GPT conversations, which is pretty great. A couple other parts of the paper that GPT breaks down for us is that 3 orders of magnitude relative to solar system standard of CI chondrites. Okay, so what the fuck is a CI chondrite? CI chondrites are a type of meteorite considered to be representative of the material from the solar system that it formed, right? So there's saying that these elements are in excess by up to 3 orders of magnitude means that these elements aren't present in quantities 1,000 times higher than would be expected based on CI chondrites. Okay, so basically these little spheres are weird. They found really weird metallic spheres, not alien, but right, all of these elements, you can probably go out and buy them on Amazon if you want it. I don't know if you can buy uranium on Amazon, but they exist here. We know what they are. There's mines for those things, right? But just the fact that they're all together inside a little spheral right at the path of this meteor is what's weird. Refractory elements are those that have high melting points and are resistant to heat. Siderophile elements are elements that tend to bond with metals. Rhenium is one such refractory siderophile element and is found at very low concentrations in these spherules. Okay. Volatile elements, here are other elements that they found, are depleted. So one thing that they found is that in these spherules, you don't have these elements, right? So volatile elements have a relatively low boiling point and can evaporate at relatively low temperatures. So manganese, zinc, and lead. So why is this important? It's because evaporation losses happen during the airburst. So when this meteor or this spacecraft is coming in and it's hitting our atmosphere and it's basically heating up and then eventually it blows up, when it blows up, these volatile elements disappear. So if you find a chunk of metal that doesn't have these volatile elements in it, what that probably tells you is that this chunk of metal came through the atmosphere from space, right? It means that it's not a chunk of metal that broke off of some rock on the ocean. It's a chunk of metal that went through this process of trying to get through our atmosphere and vaporizing all these lower elements and then only leaving kind of the stronger, more dense stuff behind in the form of these spherules. Okay. So here are all the different spherules. They labeled them all: Spherule 1, Spherule 8, Spherule 11, Spherule 13. I think they found 700 of them total, so very meticulous work, right? Someone at Harvard was literally sitting here with tweezers and going through every single one of these spherules. And then they have the different elements here. Ni is nickel, so nickel poor, low lanthanum. These are the more interesting ones here, the Belau, Belau ones. You have chondritic, and so on. So they analyzed these in 4 laboratories at Harvard University, UC Berkeley, Bruker Corporation in Germany, and the University of Technology in Papua New Guinea. So this is before we go on, this is the actual boat that they use. So this is the boat. It's called the Silver Star, and it's a catamaran. So a catamaran is a boat that basically has, it's not one hull, it's basically 2 boats with a platform in between, right? You guys have probably seen catamarans before, but this is like a pleasure catamaran, right? Like a leisure catamaran that you're just kind of like going on for sporting purposes. But the boat that they used is a kind of a workhorse catamaran. So you can see it has the 2 hulls there, and it has this big flat empty space, and this is kind of where they were trawling with that sled, right? So they rented out this boat for 14 days and then went to Papua New Guinea and trawled through the ocean. What else? They had this on hand. So this comes from Bruker Corp. So if you notice that one of the laboratories that actually performed some of the analysis comes from the Bruker Corporation in Germany. And the Bruker Corporation in Germany is the company that makes these little portable devices. So you can see here, this is kind of, you scoop the little thing. In their case, they would be putting the little spherule, you put it in there, and it kind of gives you a rough idea of what's inside this thing, right? And you can use it for, I don't know, suitcases, metal. You got some stuff, it'll tell you what's in that stuff, right? And this is the device that they had on the boat, so for initial testing. But then later on, they went and they took it into the more big boy labs at Harvard, UC Berkeley, and whatever Bruker had at their actual offices, right? And then they used kind of much more advanced and complicated tools, such as this one here, this Super Probe JXA 8230 electron probe microanalyzer, this ICAP TQ ICP-MS mass spectroscopy device. And these things are now big, right? Now we're talking about things that probably multiple millions of dollars, and they're sitting in a laboratory in Germany or in Harvard or wherever it is, right? So here's an even cooler one, a multi-collector ICP-MS. So this thing here is actually almost like a particle collider. Obviously, it's not a particle collider, but you can see that there's like 2 beams of things, and you put it right there, and it gets kind of like blasted by, I think, plasma. I'm not exactly sure. Low energy path with collision reaction cell. So there's literally a cell here that is colliding with your little samples. So pretty advanced analysis going on here. The elemental and isotropic measurements are primarily from the Harvard laboratory, specifically the Cosmochemistry Laboratory at Harvard University. So that's a pretty badass place, right? I've obviously never been to the Cosmochemistry Laboratory, but sounds like a pretty cool place to be. And this is one of the devices that I showed you, GEOL Model GXA Electron Probe Microanalyzer. And I don't know very much about this type of technology, to be honest. Probe microanalyzers, X-ray diffraction, X-ray spectroscopy, but I found this. So this is the YouTube channel for the German company Bruker, which is the exact YouTube channel, or the exact company, right, Bruker, that did some of the analysis. Bruker Corporation in Germany, right? Bruker is the company that makes this thing. And Bruker has a YouTube channel, and in that YouTube channel, they have this very cool little video where they basically show you how X-ray diffraction works. And basically TLDR is you can blast anything, any kind of piece of metal with X-rays. And when you blast it with those X-rays, the electrons will basically return X-rays. So let's see if I can get a little picture here. This one here, right? So here they have the nice little diagram. You blast it with X-rays. The electrons don't like all that extra energy, and then they're basically just going to release that energy, right? And that energy is in the form of another wave of light, right? Another X-ray. So they kind of absorb X-rays, and then they release X-rays. And then you can look at the kind of interference pattern of those X-rays, and from that, you can determine basically the elements and the spacing of the elements and different properties of the elements, and it all gets quite complicated pretty quickly, but largely what's going on is you're putting these little spherules into these little devices. These devices are kind of blasting it with X-rays and then measuring the light that comes out of it, and they're telling you what is the composition of that stuff. So that's the type of analysis that they're doing. Okay, so here's triple quad element analysis, so a different type of measurement coming from Thermo Fisher Scientific instrument. And this one's a little bit more interesting because they actually end up melting these spherules. So they don't even have these anymore. I'm pretty sure they collected them and then they took pictures of them. But then some of these measurement processes are actually destructive. So you can see here that the spherules were prepared by first individually digesting the sample. So they're literally melting these in HCl. So that's acid. So they melt them in acid and then melt them in acid again and then turn them basically into some little powder, and then that's what they're actually measuring. So it's kind of sad, but they don't even have these little spherules anymore because they basically just melted them down in order to be able to put them into these big devices here and measure them. Okay. Here's the new Sapphire, which is a third device, but largely what matters here is that all of these devices just give you different insights into the chemical composition and the elemental composition of these spherules. And in here, one thing that they mention is that there's specific ratios of iron isotopes. So an isotope is basically a type of element that it's the same element, but it has, I think, a different number of neutrons. So neutrons are kind of, if you change the number of protons in an element, it'll become the next element. So the ordering in the periodic table, I think, is basically just the number of protons. But the number of neutrons in it can change. And I think, for example, iron, you can have iron with 56 neutrons and iron with 54 neutrons, right? And the ratio between those, so this delta 5654 iron and delta 5754 iron kind of tell you something, right? Metals that come from Earth have a specific isotope ratio. Metals that come from Mars have a specific isotope ratio. Metals that come from a volcano have a specific isotope ratio. So this device here, the new Sapphire inductively coupled plasma mass spectrometer, which is the one here that where they collide this plasma in this little collision chamber. This thing will tell you the ratios between those, right? So that's what they're doing here. There you go. That's basically the ratio here of measured and the ratio relative to the same ratio in a standard sample. Okay, so now we're going to go into a little bit more deep dive into the actual spherules themselves. So this is a picture of one of the spherules, kind of really cool looking, but again, the sad thing is this probably doesn't even exist anymore because they had to melt it down in order to, or not melt it down, but dissolve it in acid in order to put it into one of these devices. But why are they spherules and why are they metallic, right? And the reason for that is that whenever this meteor or alien spacecraft basically vaporizes in the atmosphere, some of the liquid drops engulf smaller ones which solidified earlier, right? And the dendritic textures of these spherules suggest rapid cooling. Dendrites are a part of the neuron. So it just basically means a branching pattern, right? So here this is the dendrite. You can see how it kind of looks like the roots of a tree or the branches of a tree. So the dendritic pattern that they're referring to here suggests that it basically rapidly cooled, right? And that's this kind of weird, kind of like cellular looking pattern here, right? You see those kind of look like dendrites, right? Right there, there's a dendrite, and then there's the kind of dendritic pattern there. But here they're kind of more specifically talking about this, which is also a spheral, but it's a spheral composed of multiple spherules, right? And they kind of like join together. And apparently that's something that happens when you vaporize a large amount of metal in the atmosphere. Basically, some of the spherules cool faster, and then they kind of get hit by other spherules, and you get these kind of weird kind of triple spherules, right? And actually, the crazier part is that you can look at these triple spherules and then get an idea of the likelihood or other parameters of the asteroid, right? So you can say, okay, well, if the spherules are joined together in this particular way, it means that we can, right, we have some idea of like the explosion and when it occurred and like the density of the spherules, the radius of the object, and we can basically come up with kind of recreate the collision or the moment at which it basically exploded and those little tiny spherules hit each other and solidified and then fell into the ocean and were eventually found by this sled. So lots of crazy stuff here. I didn't realize you could come to all these kind of conclusions just by looking at the metallic spherules like that. But here we have the chemical composition of these. For example, here, these are different parts of this spheral. So here you have part 1, part 2, part 3, part 4, part 5. I suspect that in maybe this instrument, you basically have to you point it at a very specific part of the spheral, and then you can measure the properties of that specific part. So if you actually look at these, it seems like most of the chemical composition is basically iron. So it's overwhelmingly iron, right? 70% by weight, 50% by weight, 99% by weight, and so on. Okay. Now in this section, they basically start talking about kind of why this specific type of spheral, what they call the BELAU type of spheral, is unusual, right? So there's apparently a classification system for spherules. There's what's called S-type spherules, S-type chondritic spherules, and I-type chondritic spherules. And these come from other previous work, right? There's people that have been looking at metallic meteoric spherules for a while now. There's kind of like a whole literature for this. So here, GPT's summary of this. S-type chondritic spherules refers to a type of small spherical particle found in meteoric material that have compositions similar to S-type silicaceous chondrites. So apparently that's where S-type comes from. But what is a chondrite? A chondrite is a type of stony meteorite that has not undergone melting or differentiation, meaning that they are essentially primitive material left over from the formation of the solar system. S-type chondritic spherules are silicaceous or stony, right? Silica is the material that makes up sand, right? It's also the material that makes up our computer chips, right? Silicon or stone. S-type chondrites are rich in silicates and metal, but they differ from other chondrites in their specific mineral compositions. They are named S-types because they are highly reflective and their spectra are similar to that of stony silicaceous asteroids. Okay, so S-type chondritic materials is stuff that we've seen before, basically. Stuff that other people have seen. It's silica. We've seen it in a bunch of meteors before. The paragraph also mentions I-type spherules, which are presumably have a different composition along with their information on the nickel content, indicating that they come from a body that has undergone geological processes separating its material into layers based on density or composition. Okay. But the more interesting kind of thing in this paragraph here is that they come up with a new type of spherules. So there's I-type spherules and S-type spherules, which are present already in the literature and explainable by whatever previous science. But now we have a new type of spheral. It's called a D-type spheral. And these have never been described in the cosmic spheral literature. So now we're talking about something new. This is now a new type of spheral that we haven't seen before, right? And they further break this down into two subtypes. They call it the low lanthanum and the beryllium lanthanum uranium, or the BELAU. So the BELAU spherules have a refractory lithophile element. So if phile means lover and lithophile maybe lover of lithium, something like that, I don't know. Element abundances that are 80 to 1,000 times higher than in CI chondrites. These highly enriched BELAU spherules enriched in beryllium, lanthanum, and uranium, among many other refractory lithophile elements. Okay, so these are starting to be weird, right? Something's happening. These spherules do not fit into the previous classification system of spherules with S-types and I-types. We are now creating a new type of spherule called a D-type, and this D-type is this BeLaU. Okay. Beryllium, lanthanum, and uranium appear to have an exotic composition different from other solar system materials. Okay, so now it's not just this is a weird spheral, this is a weird spheral, and I don't think it's from this solar system. It's outside of this solar system, right? And how do we know that it's outside of this solar system? Because the abundance pattern, right, the specific ratio of beryllium, lanthanum, and uranium with regard to the rest of the actual little Ferris spheral implies derivation from a planetary crust highly enriched in refractory lithophile elements. So it's weird, right? Very low content elements suggest a source planet with an iron core, and our planet has an iron core. So some weird stuff going on here, right? They're like, not only is this not from our solar system, but this probably comes from a planet that has an iron core, which is what our planet has. Okay, so the mystery deepens. So you have a bunch of charts here that basically show you the relative concentration of different things. So each of these lines is different spherules, but I found these to be kind of way too busy. Like, just there's too much crap here. Like you're plotting like 20 lines all on top of each other, so it's kind of impossible to see. And I thought this one was the better plot. So this is figure 11. Here we have all the different spherules and the relative concentration of manganese, I guess, Mg, and then lanthanum right here. And they show you the different types. So if you remember, the I-type and the S-type are the types that are already present in the literature, right? So if you look at other meteoric spheral analysis papers, they find these S-types and I-types, and that's this green dots here and this red dots here. So you can see how there's very clearly kind of, they're down here. But the D-type, which is the new type of spheral, which they introduce in this paper, this is new, right? Look at that. That's not, there's no overlap. There isn't like, it's not like these pink dots and these yellow dots are down here, right? It's not like they're encompassed. You now have something that's kind of separate from what already exists. Pretty badass. Okay. Here are the spherules that are results for 57 spherules, blah, blah, blah. How many of the spherules are S-type, I-type, D-type, and so on. Kind of another interesting point here. Earth's upper continental crust, kimberlites, magma ocean residual liquid, sherroggites from Mars, and eucrites from Vesta. So they compared this to a bunch of weird stuff. These are, here we go. Let me see if I can find it, but here we go. So this is the element abundance patterns for a bunch of other stuff. So they have, for example, a sherroggite from Mars. They compared the element abundance pattern to a piece of Mars, right? So they literally have that. They can just scan a piece of Mars. They compare it to a piece of the upper continental crust, to whatever a eucrite is, or a lunar. So they have a lunar rock, right? So they're not, they're going beyond just like a, this doesn't look like something from Earth. Now they're saying this doesn't look like anything from Mars, and it doesn't look like anything from the moon, and it doesn't look like anything from weird parts of Earth as well, right? So like they talk about some part of a specific volcano or something like that. Where is it here? Magma ocean residual, lunar magma ocean residual liquid, right? Do not match the smooth pattern of the upper continental crust. So where did this stuff come from, right? Like, where did this come from? This is starting to be very weird. And why is it right exactly where that interstellar meteor that the DoD tracked is supposedly vaporized, right? So that's kind of the weird coincidence there. Okay, so they compared it to, I guess, a sugarite comes from a Los Angeles meteorite. So I guess sugarite is the name of a guy, Shergatti. And this person analyzed a meteorite from Los Angeles, I guess in 1998, and that's this one here, the sugarite, which they eventually figured out comes from Mars. Okay. So not only is the elemental abundance pattern, right, which is the relative ratio of beryllium, lanthanum, and uranium, weird, and it doesn't look like anything from Earth, and it doesn't look like anything from Mars or the moon or anything like that, so we can conclude that that piece of evidence at least is telling us that it's outside of our solar system. But now, if we actually look at the iron isotope, right, which is the ratios of these different types of irons, that gives us another piece of data, and that also, cutting to the chase, is outside the range of typical values for planetary basalts from Mars, Earth, Moon, Vesta, and the parent bodies of Angrites and Uralites. So, two pieces of evidence now, right? We have one, the elemental abundance pattern, and now the iron isotope ratios are also different. And here they, for example, show you so a standard terrestrial magnetite sample. The ratio of iron 56 to iron 54 is about 0.2. If you compare that to the Belau spheral, it's about 1. So you can see how these numbers here, 0.2, 0.20, negative 0.38, are different from the iron isotope ratios that you find here in the Belau spherals. It's also different from the iron isotope ratios that you find in S-type spherals and I-type spherals, which are the spherals that we do understand. So other meteors that have fallen into Earth and have been classified before in the rich history of meteoric spheral analysis, right? They classify these into I and S. Belau are D-type, right? So this is the new type, but I-types and S-types also have different iron isotope ratios, which is maybe how they distinguished those whenever those were discovered. Okay. What do we got here? Figure 17. Isotope ratio between 57 and 54 and 56 and 54 for spherals in table 6. All spherals lie outside the box in the diagram of the left panel. And this box represents the rocks in Earth. Right? So here they're saying that most of the rocks on Earth are inside this range. And what is this? This is here you have the ratio of 56 to 54 iron and the ratio of 57 to 54 iron. So if you went to your backyard and you grabbed some random piece of rock, you would expect it to fall right there. And all of the, some of these spherals fall outside of that. Right? The Belau ones, these green ones here. S21, S10. And here you have kind of a similar thing here. So here are rocks from Mars, rocks from Earth, rocks from the Moon, rocks from the upper continental crust, hydrothermal magnetite here at the very bottom. So hydrothermal magnetite, maybe that means rock from one of those hydrothermal vents at the very bottom of the ocean. So that thing looks a little weird, right? Okay. Volatile elements, so now we're kind of talking about something that GPT already explained to us, but here it is in the paper. The volatile elements such as manganese, zinc, and lead were most likely lost by evaporation during IM-1's passage through the Earth's lower atmosphere. So kind of an interesting historical tidbit, right? Lead was used in antiquity all the time for all kinds of things, right? And why was lead used? Well, one of the reasons it's used is because it's a very low melting point. It's very easy to melt lead, right? So if you're a Roman, if you're living with Roman era technology, it's a lot easier to melt lead into plates than it is to melt titanium, right? So the fact that lead is very easy to melt means that that's also why it is a volatile element, so it kind of evaporates as soon as you kind of start going through the atmosphere. The Belau elemental abundance pattern does not match terrestrial alloys, fallouts from nuclear explosions, magma ocean abundances of Earth, its moon, or Mars, or any other natural meteorites in the solar system. So, there you go. There's the conclusion. And we also know that this meteorite had a very high speed, which is challenging to explain by common dynamical processes. So this is not data that's coming from Avi Loeb's work, right? This is data that's coming from the Department of Defense kind of missile defense systems, right? They're the ones that actually release that CNOS catalog that has all of the different things that are all the different meteors that are coming into our system. And they said that this particular meteor had not only was it particularly dense, but it also had a very high speed, which they're saying here is kind of weird, right? Like where the fuck did this super fast moving, super densely metallic meteor come from? So could perhaps have instead originated from fragmentation and ejection of a core collapse supernova or neutron star mergers. So that's another pretty badass story, right? Maybe this isn't aliens. Maybe this is basically a chunk from a supernova. So a supernova is kind of like this explosion in space, and millions or billions of years ago, a supernova happened and it exploded, and the huge chunk of some Earth-like planet that was nearby that star that was going supernova, it just got shattered, and boom, that little chunk of metallic, of that metallic little Earth-like planet that was close to that star, that supernova, flew through space, and it flew through space for millions and millions of years, and then eventually went into our solar system, and then into our atmosphere, vaporized into a bunch of spherules, and then fell into the bottom of the ocean here in Papua New Guinea. And then this guy comes in 2023 with a bunch of magnets on the back of a sled and picks up one of those spherules. So even if it's not aliens, that's a pretty badass story, badass origin story for these little metallic spherules. Maybe a different origin here is an asymptotic giant branch star. I don't know enough about kind of cosmology to know what that is, but actually, why don't we search that out? Asymptotic giant branch star. Asymptotic giant branch is a region of the Hertzsprung-Russell diagram that contains evolved, cool, luminous stars. Okay, so kind of more mature stars. It's like the retirement home of stars. The final evolutionary stage of low and intermediate mass stars. These stars have between 0.5 and 8 solar masses. Core is made out of inert carbon and surrounded by a helium-burning shell. They differ from red giants in that red giants only have one shell source, while AGB have 2 shell sources. Okay, and this kind of makes sense, right? If they're guessing that this comes from a supernova, it would make sense that it comes from a supernova from a place that has a bunch of retired stars, right? They're saying here that AGB stars are kind of like the final evolutionary stage of stars, and again, the death of a star is the supernova, so that kind of makes sense. No competing interests. I don't know what that means, but I really don't know what that means. And this comes from the Galileo project. So the Galileo project is the kind of project that's being spearheaded by Avi Loeb. You can tell that this kind of work here is, in some sense, a publicity kind of gathering exercise in order to spur interest, private interest. We already know that all this work was funded privately, so it makes sense that releasing this paper, going on a bunch of podcasts, talking about this paper, really what Avi Loeb's trying to do here is get funding for this Galileo project, which he's doing at Harvard. I think the Galileo project is not about so here you go. Here's everybody at the Galileo project. Look at all these fine scientists here. But this thing is more about pointing cameras at space than it is about going to the Papua New Guinea ocean and finding spherules. I think here they're at the Harvard Observatory, so this is the part of Harvard where you can go and observe stars. And I think they have they added these extra little sensors there, and they're kind of trying to scan. And I think they actually do a bunch of computer vision as well. So they're trying to use computer vision in order to basically scan the sky for extraterrestrial technology signatures. So if you guys are interested in computer vision and you have that skill set, you can actually apply for this project. So you could be one of the scientists working on trying to find aliens in the sky. You could be developing the vision transformer that is running inside this little camera here, right? And it's not actually running inside that camera. It would be running on a separate device. But I don't even know if they're using vision transformers, right? Maybe they're using ConvNets. Maybe you're the person that's going to go there and tell them that, hey, you guys shouldn't be using ConvNets. You should be using a pre-trained vision transformer. But that is largely the paper, guys. I know this is pretty fast. We kind of got this in pretty much 1 hour. Here's even more raw data if you want that. And another interesting part that they put in this paper that I thought was kind of cool is here in the appendix section, they literally talk about everything in the boat, how they did it, and the entire process, like down to the point of like 1 hose with adjustable spray nozzle, 1 times logbook and pencil, 5 times tweezers, like 30-liter container. Tape a piece in front of the collection bucket with the name collection. Add 50 milliliters of fresh water. Like, tape a piece of paper in front of the particle sieve with the following. Like, this paper is exhaustive. It's like when you're publishing work like this, that's kind of like suggesting alien stuff. There's such a stigma around alien stuff that this paper is a very good example of extremely thorough and meticulous science, where like literally every part of this is this is exactly what we did. This is the measurement uncertainty for what we did. Here's all the previous literature on what we did. Here's the exact devices that we used. So they're being very careful, but it's also, that makes it very good science because I know exactly what they did, right? Using the tweezers, spread out magnetic sediment when dry. Sediment should not clump together. 1 tray. Lift the sheet of paper with non-magnetic sediment and pour the material into a transparent glass vial, blah, blah, blah. So you could recreate this in your own house. Here we have some more pictures of the spherules. Spheral 14 from Run 8. Run 8 was the one where they found most of the spherules, right? Not most, but the highest amount of spherules. You have this dendritic structure. Kind of cool. Right, we could be looking at a mangled, vaporized piece of an alien spacecraft here. Or we could be looking at the chunk of a planet that exploded as part of a supernova. Either one of those origin stories is badass. What do we got here? More electron microscopy, I guess. Scanning electron microscopy of Spheral S4, also from Run 8. Look at these microspherules here. Look at these little microspherules. And this is kind of in the earlier paper, right? They were describing how whenever this thing vaporizes, the different vaporization elements, I guess, are going to condense into spherules at different rates. And then those spherules will kind of stick together based on kind of the explosion itself. So just the kind of placement of these little microspherules within this larger spherule give you a little hint as to the explosion itself too, which is kind of cool. There's another spherule. Pretty cool stuff, guys. What else? Do I have any other links for you guys? Here, links to the instruments, the X-ray diffraction video, which I think is really great. You guys should watch this. It's only 4 minutes long, and it basically explains X-ray diffraction. Very great little video. And these conversations. So I found this Dr. Brian Keating. He's a YouTuber, basically, who also seems to be related to this kind of astronomy type projects, but he has 2 conversations with this guy, the Avi Loeb guy who wrote this paper. He writes his name down as Abraham Loeb. I don't know why he does that. Usually scientists try to use the same name, right? Because they want SEO. They want that SEO. They want it to be easy to find their name. So I don't know why he signs his papers using his like kind of full name, but then he goes on podcasts with his kind of short name. That seems a little weird to me. But anyways, he has some pretty long podcasts here where he talks about the project and kind of what they did, some cool facts, what it means, and so on. I would recommend those. Those are pretty great as well. Right on the 1 hour mark, we're going to end it there. You know, I know it feels a little unsatisfying. Usually this channel is all about super deep 2 hour deep dives, but this isn't a machine learning paper, so I don't really have a ton of expertise here. I'm just interested, curious scientist who just saw this kind of cool alien paper, and I was like, I got to kind of read through this and see what's happening. But, I don't really have very good insights for you guys other than just what's in this paper. Let me take a sip of this yerba mate, and then I'll give you guys a summary, and then we'll sign off. All right. So here's a summary. Today we reviewed this paper called Discovery of Spherules of Likely Extrasolar Composition in the Pacific Ocean Site of the CNOS 2014-01 IM1 Bolide. Okay, so in this paper, Avi Loeb and a bunch of other people from Harvard and from Berkeley and from the Papua New Guinea University went to Papua New Guinea, specifically this kind of patch of ocean over here, and they trawled a magnetic sled through the sediment, right? So they took this magnetic sled and they trawled it through the sediment. Why did they go to this specific region? They went to this specific region because CNOS, which is basically Department of Defense, NASA, it's, let me actually give you the exact name here. CNOS is the Center for Near-Earth Object Studies, basically U.S. government organization that releases this catalog, I guess, with basically every single meteor that hits the Earth and where it hits it and where it is. So they went to the exact area where the CNOS is telling them that this meteor is, and this meteor was already kind of weird because it was traveling very, very quickly, and it managed to penetrate our atmosphere particularly deeply, which means that it had to be very dense, right? If a meteor is very fragile, it'll very quickly vaporize, but this one managed to kind of penetrate a little deeper, which means that, okay, something's going on here, right? So they went to this exact place. So the DOD is telling them it's inside this square area is where you're going to find all the vaporized pieces of this meteorite. And I think that they're very clever, right? They keep using the word bolide, right? So they keep using the word bolide and not meteor, right? If they wanted to basically put into your mind the idea that this is a meteor, they would have just called it a meteor. But they call it a bolide because they want to make you think that, hey, maybe this isn't a meteor. Maybe this is a Voyager probe from an alien civilization, or maybe this is a Voyager or an alien spacecraft. So I think it's a clever choice of the word bolide there. And what they do in this paper is they collect these little spherules, and then they basically put them through a barrage of tests where they run them through a bunch of these fancy machines, X-ray diffraction machines, spectroscopy machines, whatever an ICP-MS machine is. And basically, these machines will tell you the element composition of these. So what are the elements that make up this thing? And it'll also tell you more fancy things, such as what is the ratio of different isotopes of iron. And whenever they look at the elemental composition of these and the ratios of the iron isotopes, pretty much all of those pieces of data support the fact that these are weird spherules. These are not from Earth. These are not even from our solar planet or our solar system, right? And they compare it to stones from Mars, from stones from the moon, from other meteors, and they don't look like any of those, right? And specifically, they call these type D spherules. So other people have been studying spherules from meteors for a while now, and they generally tend to fall into what are called I-type or S-type spherules, and these are a new type of spherule called D-type spherules, and they're basically made up of beryllium, lanthanum, and uranium, and they have a weird iron isotope ratio. Here's some more plots, and I think the very bottom is kind of here once we go to the actual conclusion. So the two, here's where they discuss and they conclude, and they kind of come to two different conclusions. So it could have originated from basically a iron-rich planet that exploded as part of a supernova within a asymptotic giant branch star. So this is possibly the most kind of like vanilla or mainstream explanation as to what these spherules are, but may reflect an extraterrestrial technological origin. So they waited until the very end of the paper, which is a very sober, very dry, very meticulous scientific paper, to give you that little tidbit of alien juice at the very end there that maybe these are extraterrestrial technology. And that's the paper, guys. Pretty cool little work there. Do we have a diffusion paper next week? Yes. Hopefully we go back to machine learning, but I don't know. If this video gets a bajillion views and suddenly everyone's interested, because aliens are hot right now, then I don't know. Maybe I'll have to read another alien paper. I try not to get audience captured. I try to read the papers that I'm interested in, but I'm also a slave to the algorithm. So if it's aliens that people want to talk about, it's aliens that I'm going to talk about. Hope you guys found that interesting. Thank you, Ed. Thank you, John. Thank you, Josh, Eugene, Joseph, RandomBot44, Khalil, Riddell. Thank you for the questions. Thank you for hanging out. Hope you guys have a great Sunday, and see you guys later. Let's announce the end of this session.